So my idea was that I know most people in this audience are going to be familiar with what tropical geometry is, but I just wanted to give a brief 3-minute summary of tropical geometry so that everyone who is not familiar has some basic idea that they can follow throughout the talk. So consider this as a chapter 0. So tropical geometry is a particular flavor of geometry without geometry, where you have geometric objects that you want to learn more about, and you want to learn more about them using methods that are not really geometric in nature, because geometry is hard and other methods might be easier. Dante, you look concerned. Is everything okay? So the idea is you have some algebraic geometric object. Then you construct a combinatorial analog of such an object. You study this combinatorial analog using combinatorial methods, get combinatorial results that translate into algebraic results. So usually the way you do this is by working over a field with valuation. For instance, the Puiseux series, so the complex Puiseux series for today, which are essentially power series that have a lowest element. And this valuation map maps you from this field of valuations into the tropical numbers, which is just R union infinity, where you map a function, a power series, to its lowest exponent. So this is what you do with the coefficients of your polynomials. And if you now have a polynomial over such a field with valuation, what you do is you translate this into a tropical polynomial by substituting coefficients with their valuations. So if f can be written as the sum over alpha in the natural numbers, C alpha x to the alpha, what you do is you substitute the C alphas by their valuation, and you substitute sum and times by tropical operations, which I will denote as tropical plus. This is the minimum of all the elements. And you substitute every multiplication by tropical times, which is classical addition. This way you obtain some kind of piecewise polynomial object that you can translate into a polyhedral object by taking its tropical variety. And this tropical hypersurface is just the set of points, the set of alphas, the set of entries for x, where this minimum is attained at least twice. So V of a tropical polynomial is the set of x such that the minimum in trop f of x is attained at least twice. For our field with valuation for the Poisson series that we have here, this is just where this is just the set where the lowest terms of your coefficients of your Poisson series are equal, which means they could cancel out in theory. And this is a polyhedral complex. And now people have studied this polyhedral complex and used it to come up with different geometric statements about varieties. And today we are going to construct similar combinatorial analogues that are very much inspired by this for an object in geometric representation theory called a Quiver Grassmannian. So let me start out by defining what are Quiver Grassmannians. For that, I should tell you what a quiver is. I'm sorry, I'm a bit too short for this board setup. So a quiver is just a combinatorial object that you're all familiar with. It's just a directed graph. So quiver Q with vertices V, arrows A, source and target maps for your alpha, for your arrows, is a directed graph. And because we are having now a chain of definitions, we're going to have a chain of definitions. Let's keep track of a few examples on this board here. And we're going to need the examples throughout the entire talk. So if I at some point start to clean this board, please shout at me and tell me off. So the two examples we are going to look at mostly today are the following two. One where you just have two vertices and a parallel arrow in between. And then one that looks kind of like an extension of this picture, where you have 4 vertices and 4 arrows that also go in the same direction. And I should say, in our case here, we allow for all kinds of nastiness in our quiver. We allow for these vertices, we allow for this graph to be disconnected, we allow for loops, we, as you can see, allow for parallel edges. We don't care as long as you can write it down as some kind of directed graph. Now we endow this combinatorial object with algebraic information by assigning algebraic information to each of the entries here, so to the vertices and to the arrows. Now a quiver representation R is an assignment of vector spaces v small v to vertices and of compatible linear maps between those vector spaces to the arrows. Linear maps f alpha from the source of alpha into the target of alpha for all alpha in my set of arrows. So in our example, let's assign 2 different vector spaces here. So here I would like you to consider the field of Poisson series squared. So we have some kind of nice field with non-trivial valuation. And for here, I would like you to consider C4, which is just your standard complex numbers. They do have a valuation. It's the trivial valuation. So if I do this tropicalization procedure I told you about at the beginning, every coefficient just gets mapped to 0. Okay. Now these quiver representations are nice, but we want to construct some kind of parameter space of quiver representations. And for that, it makes sense to consider Quiver subrepresentations. A Quiver subrepresentation where this is my original Quiver representation over here, is now a collection of subspaces of my representation such that everything still makes sense, so that they still form a representation.
Isn't here like elements from A, right?
Sorry?
Those are elements from A, right?
No, S and T are the source of alpha and the target of alpha, which are elements of V. Is a collection of subspaces NV for all of my vertices V, such that F alpha F alpha of N source of alpha is contained inside of NT alpha. So that your picture here, you still have some compatible maps. And I forgot to tell you what my maps are going to be. They are all going to be the identity for now. And now the Quiver Grassmannian, as I already spoiled you a few minutes ago, the Quiver Grassmannian is the parameter space of all these Quiver subrepresentations with respect to a fixed dimension vector. Where you have that, so of course, subrepresentations such that the dimensions of my constituent vector spaces are equal to this dimension vector dv here. So for this brief discussion, let me just give you an example of a Quiver Grassmannian most of you will already know. So the easiest Quiver Grassmannian you could come up with is what happens if you just put a vertex here with no maps. That corresponds to the ordinary Grassmannian. Now, if I have a chain of vertices with identity maps in between them, this corresponds to the flag variety that you know. Now, this would be, if I put something of dimension 4 here, this would be the complete flag variety. If I assign the correct dimension vectors. But you could also turn this into partial flag varieties. So why should you care about this? The first reason is from a combinatorial point of view, you can use these quivers to describe very interesting different types of combinatorial arrangements. Essentially, every arrangement between linear spaces that you can describe in some way using linear maps, even if there's many of them, you can describe here, is essentially as long as you don't care about lengths, like about how far apart points are in some kind of line arrangement. This describes the parameter space of such things. So these are combinatorially interesting. But they are also interesting from an algebraic geometry point of view. And you can, so there's a result from Reinecke from the early 2010s that every projective variety you can express as the Quiver Grassmannian as of a certain quiver. Yes? So the dimension at each of the vertices is indicated by this dimension vector v here. So D is a vector, yes. And it has as many entries as you have vertices. So maybe in. Sure. You will see on the tropical side, you will see this later. On the algebraic geometry side, right now, if I just have this multiple edges and it has the same map assigned to it, this is just the same as if I had just had one map. But I could feasibly assign two different maps to it, and then I get different representations. So this is the first example here is actually a very problematic example in Quiver theory often, because you have infinitely many different representation classes. So you can show that Quiver representations are isomorphic if you can write a map between all of the vertices such that it compatibly changes. But you can, if you put the identity map up top and another map that has a different, that is of the full rank but has a different, is not the identity map, then you get infinitely many different representation classes. Just if you put the identity, it doesn't matter, but we'll see on the tropical side how it does matter. Yeah. Any more questions? So there's a theorem by Reinecke that tells you that every projective variety is a Grassmannian, is isomorphic to. Now, the representation that Reinecke constructs, it's a constructive argument, but the representation that Reinecke constructs is rather ugly from a Quiver perspective. So it has very, very many parallel arrows because it essentially uses the Veronese embedding to construct its Quiver Grassmannian. So usually if you want to study Quiver Grassmannians and geometric representation theory, what you do is you restrict yourself to projective varieties that have a nicer associated Quiver representation. So for instance, there is a paper by Alistair Craw and Greg Smith that does this for all toric varieties, where your associated Quiver is much nicer. So every projective, so it's the same essentially where you insert toric before variety projective. And then you can use this to study line bundles and things like that. So these have a nice geometrical structure as well. So it makes sense that one might want to study them, but they are also quite combinatorial. So there's hope that using tropical geometry, you can find out some more about the combinatorial structure of these objects. Good. So let me get started. Now, yeah. So you will see this a little bit later in my talk. The easiest way to see this is there are explicit equations for this projective variety. That's the way I'm going to do it later on. It's a projective variety in the scheme sense, yes. It's also a projective variety in the embedded sense, but it's in both. So to construct a tropical analog, I have to tell you, essentially tropically, what do you put on the vertices and what do you put on the arrows? And now in algebraic geometry, what we put on the vertices, or as the representatives here, are linear spaces. So it makes sense to consider tropical linear spaces as the object you put on your vertices, which Alex thankfully introduced earlier today, but I'm going to look at them from a completely different point of view with completely different cryptomorphisms. So, but the objects are the same as the ones Alex discussed. So let's construct tropical linear spaces. And for that, I will tell you what a evaluated matroid is from my point of view. So evaluated matroid mu is a map from the set of subsets of n, where this is just the set 1 up to n, of size r into R union infinity, where you have the following two properties. First off, you don't want this map to just be the infinity map. So mu not equal to infinity. So it doesn't map everything to infinity. And more importantly, you have a basis exchange axiom. So for all I and j in n choose R, and I in I set minus j, there exists some kind of j in j without I, where the valuation of I plus the valuation of j greater than or equal to the valuation of I, where I exchange my small I for this j, plus the valuation where I exchange my small j for the. And now you can show that this is equivalent to the subdivision notion that Alex did by essentially showing that these things define your height function on the matroid polytope. And these define, in fact, all height functions. But if you come at it from a more linear algebra perspective, I'll just give you an example on how you would construct a evaluated matroid given a matrix over a evaluated field. Any more questions up until now? So let's consider an example. And for the example, I need my notes so that I can write down the correct matrix to get a nice and easy valuation. So we consider the following matrix over the field of Poisson series. Now, if you take this matrix, you obtain a evaluated matroid by assigning numbers to your columns and then taking the corresponding minors. So mu of 1, 2 would be the valuation of the minor that you have here, which is just A. You can further do this for 1, 3 with the evaluation of t to the A, which is just A, the evaluation of B plus A, and for 2, 3, you have A squared here, so t to the A, t to the 2A, which is going to be 2A. And since we are essentially projective, we can rescale all this by the same number, so we obtain an equivalent evaluated matroid mu tilde, where this has valuation 0, this has valuation B, and this has 2, 3 has valuation A. And you can, if you want to, if you have time, you can check that this is actually a valuation in the sense that we had seen before. Now, this doesn't look very polyhedral, and tropical geometry objects are usually polyhedral. So how do we get from there to something polyhedral? And that's via using co-circuits, via using circuits. So we look at all, so my evaluated matroid has a rank, just like a usual matroid has a rank. And for the circuits, we look at the sets of size 1 bigger than the rank. So for every mu tilde is an equivalent evaluated matroid. So mu tilde is the same, is evaluated matroid as well. And it's the same evaluated matroid as the one here by rescaling every single valuation by A. So for every I in N choose R plus 1, consider C mu I to be a vector in Rn that has entries I set valuation of I set minus I if I is an I, and infinity otherwise. And this gives you now a coefficient vector of something that cuts out a tropical hypersurface. So the tropical linear space prop mu is the tropical pre-variety cut out by linear functions where all of your coefficients are the entries of these circuits, is the intersection over V of Ci tropical times Xi inside of Rn. So let's consider this for our example. We can already compute this while I clean the board. So in our example, there's only one subset of 1 to 3 with of size 3, namely the set 1 to 3. So there's only one circuit, and your tropical linear space is cut out by precisely one equation, namely the equation that this thing gives you. And these, essentially what this equation does is it reverses the order of your circuits in the way I wrote them down for you. So let me write this down less nebulously. Continue our example. We consider the circuit mu tilde of 1, 2, 3. So the first entry of the circuit is what happens when we delete 1 from the set 1, 2, 3. So we obtain the valuation of 2, 3, which is just A by this thing here. Now, if we delete 2 from our circuit, we obtain the valuation of 1, 3, which is B. And finally, if we delete 3 from our circuit, we obtain the valuation of 1, 2, which is just 0. So the corresponding tropical linear space is the tropical linear space cut out by A tropical times X, tropical plus B tropical times Y, tropical plus Z, tropical times 0, which is the same as Z. And now if you know about tropical geometry and you have seen this before, this is just your standard tropical line where you're rooted at the point minus A minus B here. Good. Yes. Intersection is set theoretical intersection. Oh, this is over all the circuits. So every circuit defines such a function. You take the intersection over all the circuits. You obtain a tropical group variety. Yes. The circuit from your mu is this construction here. So you take this vector where for these sets of size 1 bigger, you look at what the valuation of the basis looks like when you delete the element out. Okay.
Usually one intersection over the subset I.
That's the same thing as the intersection over all the circuits.
Same thing, but maybe someone that doesn't know.
Okay, yeah, sure. I can write it down that way if you think that's more helpful. So you can also write this down as. Is this helpful? Yes. Yes.
Then in the sum,
Mhm.
how do I have n entries in my vector, not r+1?
You have n entries because everything that is not deleted out gets assigned infinity. So in the polynomial is actually of length r, or slightly smaller than r if some things have valuation infinity. But yeah. Okay, so now that I told you what you should put on the vertices, let me maybe tell you what you should put on the arrows, and this is where things start. So everything I've told you about here is essentially standard theory from Speyer, as you already know from Alex, from the 2000s, 2010s. And this is newer stuff. So what do you put on the arrows? And I'll propose 2 different things. But let's start first with morphisms. So this is approaching the topic from a perspective that makes sense from the point of view of valuated matroids. For that, we should consider if we have a quiver, and I have deleted my quivers and nobody has shouted at me. Oh well. If I look at my quivers here, what would I want to put on the vertices for my big space where I want to take subspaces of? So in our example here, we know that these tropical linear spaces are what we would substitute for the subspaces. So what do we put on the actual vertices? And the most straightforward interpretation of this is we want to put n on here. This is almost correct. So if we put n on here, we obtain almost the correct picture. The issue we run into is that if I take a map from n to n, matroids don't know what it means to map to 0. Now, mapping to 0 is quite essential for a lot of linear maps. So what I do is I extend my ground set just by adding an element that is a loop in matroid theory, which you should consider as equivalent to a 0 vector in linear algebra. So that allows me to map something to 0, some element, some coefficient to 0. And further, what I want to do is I want to also describe some kind of affine map. So I will allow this map from n to be augmented by some kind of real number. So let's consider the setup. Now this defines a map of ground sets. And if this map of ground sets now is compatible enough with my valuated matroids, I say that this is a morphism of valuated matroids. So what does compatible enough mean? A morphism. Let me do it this way. So every such map defines a valuated matroid. If I have such a map from a valuated matroid to another one, this defines a third valuated matroid. So let me consider the map from nu into mu here. And consider the matroid, the evaluated matroid that is induced by this map. So the induced evaluated matroid is the function f to the -1 of mu that is defined on sets as mu of f of s. So if I want to evaluate it as a set, I look at what the image of that set is in under my map f here. And because I have this augmented coordinate, it's the first coordinate, plus I sum over all the augmentation factors of things that are contained in my S. Now you can show that this defines evaluated matroid, so it makes sense what I am about to say. So this is evaluated matroid. And I am saying that this is a morphism evaluated, the map F is a morphism evaluated matroid if this evaluated matroid is matroid theoretically contained inside of mu. So F is a morphism evaluated matroids if f to the -1 of mu is contained inside of a quotient of nu. Marie will tell you a lot about quotients tomorrow, I think. Yeah, tomorrow. But let me just give you a super short inequality that is equivalent to this. So this means that for all I in the set of bases of the underlying matroid of this matroid mu, and j in choose S. And all I in I set minus j, there exists some j in j set minus I, where we again have this exchange property. So where we have f to the -1 of mu of I plus f to the -1 plus mu of j is greater than or equal f to the -1 of mu of I set minus I union j plus mu of j set minus j union I. And so I have some kind of exchange property with respect to this new induced matroid that I obtain from my map here. And this is a perfectly nice setup that you can do this whole theory with that I'm going to explain to you, but it's slightly restrictive because it only describes things that make sense matroid theoretically, whereas tropical geometry also makes sense in a slightly more broad context. So this is a good enough definition, but restrictive definition of tropical linear maps. And for those in the audience that know a lot about linear tropical geometry, it will be of no surprise to you that this essentially coincides with the belief that GL trop of n is just the Sn semi-direct product with R. But tropical geometry, sorry, R to the n, yes. But tropical geometry can be a bit richer than that. And we exploit this for defining a different thing to put on the arrows and making sense of that. Any questions until now? The semi-direct product structure is essentially this augmentation by this augmentation factor in my linear map. Yeah. Yes. It's kind of like a pre-image. And the idea of why you would define a morphism in such a way is because this is one of the things that are true in linear algebra. So something is a linear map of vector spaces if the pre-image of this linear space is contained inside of the usual linear space. And pre-images are something that you can make sense of quite nicely in matroid theory. And containment is something that you can make sense of quite nicely. So that's why one would define it. One could define it that way. There are different possible definitions. So what's the other thing we can put on the arrows? The idea is that we take this GLN point of view very, very literally, and we just put matrices on the arrows. Matrices over T. Now, I should start out by telling you that conceptually this is a bad idea. So the idea is that I take a tropical linear space, I take a matrix, I do pointwise multiplication of my matrix with my tropical linear space, I obtain, hopefully, another tropical linear space. That would be the naive hope, but the problem is that this is actually not true. So A tropical times prop mu is not always a tropical linear space. And pretty badly so. So let's take the image we had seen of a tropical linear space. We have minus A, minus B here. Multiply this tropically by the map that has zeros here, infinities here. So essentially, this is just the identity map where I have one additional thing that is not zero. But if I multiply this with that tropical linear space, what I get is this object here. And if you know a little bit about tropical geometry, you know that this can never be any kind of tropical object because you cannot balance it. So not only is it not linear, it's also not tropical. But it is, in some sense, tropical enough for quivers to make sense. And for that, I should go back to the algebraic picture just briefly. And tell you how you actually give this, how you actually see that Quiver Grassmannians are projective varieties via equations. So the way you usually get equations for Grassmannians is by taking Plücker equations. And this same idea works for flat varieties as well. And due to Lorscheid and Weiss from 2019, this also works for general Quiver Grassmannians. So the idea is now that every linear map that you put on your quiver over here, you can represent, if you choose bases, you can represent by a matrix. So let's just fix the setting here that might look slightly trivial. The map from Cn to Cn, and this linear map, this map is given by a matrix A. Now, Lorscheid and Weiss say that QGR is cut out by the Docker equations for each of the vertices. And the following quiver-plucker relations for each of the arrows. So P alpha N are the sum over all J in N set minus I. I'm sorry for readability. The word here is a bit smooth. It's true. You can check it out later if you want to. So you have some kind of sign. This is not very important tropically, so I'm just not going to spell it out what it is. You multiply this with the entry of your matrix M alpha, so in our case A, associated to my arrow alpha here, at ij, which are the things you are currently permuting. And you take essentially plucker relations. So if you stare at this long enough, and you do this for all I and j of the correct size, so for all I in n choose r minus 1, where r is the rank of this thing here, and j in n choose s plus 1. If you stare at this for long enough, you realize that if I just put the identity matrix here and I have two vertices, if I take R and S to be equal, what I obtain is just the ordinary plucker equations. If I put the identity map here and my things have different ranks, what you get is the flag plucker equations or incidence plucker equations. But of course, you can use this to describe many, many different more types of plucker equations that are augmented by this matrix that describes the linear map here. And it turns out that you can translate this using this tropicalization technique I told you at the beginning. You can translate this into a polyhedral complex, and this polyhedral complex makes sense with all the different things I told you about today. So let's define this. The alpha, which subscript? Oh, the alpha is for each of these arrows. So alpha is an arrow. Maybe I should call this M alpha and unify notation because, yeah. So for each of my arrows in my quiver, enough in the example quiver that we are looking at notation-wise, here, this is just this one arrow. You can obtain such a set of equations, augmented plucker equations, and you can work with them. So the Quiverdressian QDR of a representation R with respect to some kind of matrix representation, so fixed matrices and a dimension vector D is the tropical pre-variety cut out by the tropicalizations of these quiver plucker equations. And I already told you that this makes sense with the things we have already discussed. So let me summarize this in a theorem. So Julia and I show that if I have to make, in the setting here, I have two matroids mu assigned to mu here. Let me keep notation clear. Mu here and mu here assigned to my vertices and this map M alpha. Then I have mu times nu is in this Quiver-Dressian for R and S, where maybe I'll just draw the picture here. That's clear what I mean. So where this is my Quiver representation I'm considering, if and only if the valuation of M alpha, where this is just the pointwise valuation, tropical times my trop mu is contained inside of trop mu. So in other words, the Quiver-Dressian I defined coincides with this matrix representation here. So now let me get back to the more matroidal way to look at arrows. We can interpret this result in that way as well, if our matrix is nice enough. So Julia and I show, and this is actually the most work we did in the paper. If M alpha is weakly monomial, then there exists a corresponding morphism F M, and the reverse is also true. So if you have a morphism of evaluated matroids, Fm, you can construct a weakly monomial matrix that satisfies the property we have here. If M is weakly monomial, then exists a corresponding morphism, and vice versa. So we can extend our theorem here in the cases where our matrices are particularly nice to the following statement. If M alpha is weakly monomial, this is equivalent to F from mu to nu being a morphism of evaluated matroids. And I should say this works in more generality than the way I wrote it down on the board. This works for quivers where I have different dimensions on each of the vertices. It works for quivers where I have more arrows than in this picture. It's just for notational clarity, I wrote it down in this way. In my last 5 minutes, let me tell you a little bit about how this distinguishes from the geometric case. So we started out with a projective variety, namely the Quiver Grassmannian. What we could have done, because we have a projective variety, we could have just applied tropicalization to that projective variety, taken the object that comes out there, considered that thing, and called it a tropical analog for our Quiver Grassmannians. But that gives you a different picture than the picture here. The main difference is the number of equations you are essentially cutting over. So this Quiver-Dressian is a tropical pre-variety, where you take the intersection of a finite set of generators, and the tropical variety is much more restrictive. So Julia and I prove that Q dr of R and my dimension vector D is not equal to the tropicalization of Q gr of R and D for almost every Quiver representation R. So essentially, you start finding counter examples for this starting in for ambient space dimension equal to 2. And the examples that have accompanied us through the talk are actually 2 of the counter examples for this statement here. So in our setting here, what we want to do is we want to assign at the bottom, we still stick with identity matrices. So these are just your usual friendly identity matrices. Nothing weird going on here. And for the example at the top, we just take 2 matrices that are not equal, but that tropicalize or evaluate to the same matrix. So here we would take the matrix 1, 1, 0, 0. And here we take the matrix 1, 1 plus t, 0, 0. And now you can compute that the associated Quiver Grassmannian of this thing is just the tropicalization of this Grassmannian, which is just 2 points in a product of 2 projective spaces. But the Quiver Dressian has a higher dimension already. The Quiver Dressian doesn't distinguish between those 2 matrices, so the Quiver Dressian is going to be the full line here. And for this example, I cannot draw this picture because this picture is 12-dimensional. But what you can see is you again obtain, for a relatively nice example where you don't have any kind of parallel arrows and no trickery happening with your valuation map, you obtain 2 tropical analogues of this Quiver Grassmannian that are different. And so that was my talk. Any questions?